So how do you create an oxygen minimum zone in the ocean? Okay, so in the ocean interior, there is no source of oxygen. Okay, so the only source of oxygen comes from air-sea exchange, gas exchange, plus photosynthesis in the euphotic zone. Okay, and this we can call direct ventilation, okay, in the surface layers. All right, so that's the primary source of oxygen. Mm-hmm. So now, how do you get the minimum? And it's best explained if you just approach this problem from the other side around, other way around. Okay, so how do you bring oxygen into the deep ocean? We have the North Atlantic deep water and the Antarctic bottom water. That's the deep circulation of the ocean. Okay, so there's water formed by convection in the Greenland Sea and in the Labrador Sea and on shelves in Antarctica, and they are oxygen rich. Okay, these waters are also cold, so they can take up a larger amounts of dissolved oxygen and then move it through the deep oceans. In the deep oceans, there is no light, okay, and there is little production, and which means is there is a low oxygen demand by bacteria, so the dissolved oxygen concentration can remain at high levels. Okay, so we have a maximum near the surface that I already explained, and near the bottom, and between this region is a zone which first of all has a high oxygen utilization by bacteria, okay, and also has a low ventilation by currents. So there is regions that are isolated from direct influences of the oceanic circulation. Okay, so there are two competing processes. One is one are the bacteria that use up oxygen, and the other one is the ventilation by oceanic currents. Okay, so that's all fine, except for the situation in which you have not enough oxygen in the ocean. Okay, so-called dead zones, where you cannot support different certain parts of marine life because there's just not enough oxygen there. And above my head is a table of lethal oxygen levels. Okay, for different type of marine species, crustacea, fishes, bivalve, gastropoda. Okay, and I just drew one red line which indicates an estimate of a critical level that applies to all species. So all species are more or less affected by such low concentrations. So a typical threshold for hypoxia is 60 micromoles per liter, which is equivalent to 1.4 milliliters per liter or 2 milligrams per liter. The reason why I give you these different units is because if you look at this oxygen distributions, you get different units. Again, if you need to look up what is the critical level, and then you can come back to this slide. Okay, before we go on, I just want to explain what these diagrams are that you see. Okay, these are called box and whisker plots that you see above my head. Okay, you can see a box, and you can see these lines which are like the whiskers. So how do you create these plots is you have a measurements, and you sort your measurements according to the value. So you have the smallest values in the left and the largest values at the right, and then you split up your observations into 4 quarters, 4 groups. Okay, so 25% of the lowest values, okay, and then you have, okay, that makes sense. So the box that you can see here shows you the range, which is from 25 to 27 Okay. The lowest quarter you show as a line on the left, and the highest quarter you can see on as a line on the right. What this means is that you can see the absolute maximum and the minimum of your measurements. For Crustacea, for example, you have a species, on some species which need much more oxygen. You need almost 200 micromoles per liter in order to survive. Okay, but you can also see the range for 50% of your species. Okay, you can work out what's the lowest and what's the highest level that you need. Okay, and these representations in terms of statistics are very, very useful if you want to show what is the what's the absolute range, and also what's the spread of sensitivity. So all right, so then you learned about oxygen minimum zones, and you learned about lethal oxygen levels in the ocean.